doing science so that I could become a world-renowned sensation. So you're helping me in my quest to become famous.
Wonderful. I'm doing my very best. That's great. So that's the perfect note to start the talk on. It's my great pleasure to introduce Anthony Polloreno from Boulder, Colorado in the United States, who's giving a group talk today. So he has a kind of a wide range of topics he's interested in. I mean, he has worked with the quantum industry, like with Rigetti, as far as I know, and is now a PhD student in Boulder with Graham Smith, having worked on notions of metrology, then a bit of quantum error correction, sensing in many ways, quantum approximate optimization with slow measurements, like so the full portfolio ranging from sensing to error correction and quantum near-term quantum computing. And the talk today will be on a topic of sensing in a fresh flavor, namely broadband sensing, where the kind of plain vanilla bounds that we know can be a bit refined in an interesting fashion. So thanks for coming. I mean, actually physically, but now the talk is a virtual talk, but never mind. So thanks for coming in like both on site and online. So I would say with this, the stage is all yours.
Thank you, Jens. And yeah, I've already met some of you. The others I haven't met. I might be on campus again later, if anyone else is on campus. Yeah, so thanks for the intro, Jens. The other thing I should say is I'm also interested kind of in like tomography. When I was at Rigetti, I did a lot of kind of characterization work. So building the software for kind of calibrating the chips, and then also stuff like gate set tomography. And so going forward, the last year of my PhD, I'm planning on working with Sandia, so like Robin Bloom cohort and Kevin Young, Tim Proctor to do kind of QCVV stuff. And then I guess what also Jens didn't say was I'm also writing up a project proposal with him for applying for a postdoc with this wonderful group. So I'll get started. If you have questions, comments, please jump in. Let me figure out if I can get my computer to work. I was a software engineer, so pressure's on. Can you see that?
Wonderful. We can.
Great.
See you and hear you and see your slides.
Great.
The most spoken sentence of the year.
Okay, so right, this work, maybe it's not necessary to qualify the statement, but I actually think it's pretty interesting. It's on broadband sensing, so I'll say what I mean by that in a second. But so this was done, I'm funded by NASA, also the NSF. I'm at GILA, which is a joint institute in Boulder. Come visit Boulder if you are interested. It's a beautiful place. My collaborators are on the bottom left. People from Quantinuum, which used to be Honeywell, people from GILA, and then other, people from GILA. I'll get started. Beeping noise, computer is mad. Okay, so the context that we're going to imagine is sensing a magnetic field. I think there's been, in particular, you guys just put out a paper today, but work in this group on metrology. So I think maybe we can go into more discussion if people want to be more concrete and make me think a little bit more. But I think we can acknowledge that kind of, sensing is maybe something useful to do with quantum systems, maybe more near term than say full-scale error corrected quantum computing. Also, I minimized it's nice to see people, but I minimized the picture. So if anybody is like grimacing in horror or ecstatic, I can't see your face. I'm just gonna believe that you're all thrilled with the talk. But a simple context, I guess, for sensing magnetic field is for sensing, you just imagine that you have a magnetic field to start with. So this is a box. I always say it's a quantum box because it has an atom on it. You imagine it's a quantum sensor. It's sitting in a magnetic field B. Of course, the Hamiltonian is just this for an AC magnetic field, has some frequency. And of course, even though this is a very simple model, we can imagine that is useful in contexts like a spin in a magnetic field. If you have things like a transmon, as we'll kind of talk about at the end, I mean, just a qubit really, but the thing that was coming to mind for me at the end was like CPMG kind of, you can do like noise spectroscopy. So frequency noise on like maybe a flux tunable qubit. And then we'll also talk about something like an axion coupling to a detector. I'll say specifically what I mean by that. I'm not a high energy or beyond the standard model theorist, but I have some understanding of how axions kind of couple, and I think this work also has relevancy there. So to start with, the kind of quantity, we're talking about broadband quantum sensing. How are we going to quantify what we mean by sensing? You have the quantum Fisher information, which for pure state is given by this. It's just twice the trace of the square of the derivative of the state with respect to the parameter you're trying to estimate. In the kind of simple model I've presented you, it's just a magnetic field amplitude. So you're taking the derivative with respect to the magnetic field. So this kind of intuitively is just a sensitivity because it's a derivative. It has other nice properties. But in this kind of simple picture, it's you just have a state. There's some frequency of the magnetic field that has some amplitude and it evolves for some time. One of the nice properties is that using the quantum Fisher information, you can quantify in what sense exactly it's an information by the quantum Kramer-Rao bound. So you have that the variance of any estimator using the quantum state is kind of lower bounded inversely by the information, which means that if you have a lot of information, you can kind of get an arbitrarily tight, arbitrarily low variance estimator. So that's the sense in which you want to call this an information. So just again, as a simple example for anyone who's not familiar with quantum Fisher information, you can imagine something like just the DC case. So omega equals 0, very, very simple Hamiltonian, just BZ. If you just evolve for some time t, the angle that the block vector precesses around is BT. And so if you write down the density matrix rho, you have these coherences on the off diagonal. You compute the quantum Fisher information with the derivative, and you end up with 4t squared. So this kind of example gives you quadratically much quantum Fisher information in time, which is great. And I'll take this opportunity to say that it's also known that this is optimal. This quadratic scaling with time at a particular frequency is known to be optimal. I think the paper is by Pang and Jordan. But so kind of, I'll skip ahead a bit. I'll say this in future slides, but I'll also just say it now since I believe you all to be a capable audience.
Oh, wait, but then I have a question when you challenge us. So what's the problem when you say quadratic in time? Like what's the promise on the initial state that you have? Is there one, or what's the deal?
As far as I'm aware, I think it's like, so there's a bunch of different caveats, right? Like there's like, you can have protocols which are somehow adaptive, a bunch of other things, but I think the Pang and Jordan example is something like you have, I mean, I think it's exactly this context. Like, so in the specified to the DC case, I think if you say you're just sensing a DC magnetic field and you ask, what's the best protocol I can have? So starting in any initial state, somehow this is optimal. This is obviously optimal for DC, but then for any AC protocol, I think it's like you can pick a different initial state and you're still only ever going to do kind of have t squared scaling. And I think that's probably also kind of obvious if you consider like echoing sequences.
Okay. Yeah.
But so the kind of thing that we didn't know the answer to and seemed like a nice question to ask, and is indeed the question we're going to answer, is if you have, instead of just trying to build a sensor that detects at one frequency, you want to build a sensor that kind of performs well at many frequencies. So you don't know the frequency of the magnetic field that you're going to get, and you're not going to adapt your measurement strategy, but you kind of want to be able to like put this box in the field of unknown frequency and kind of perform and be able to get an estimate of the magnetic field at many different frequencies. What's the best you can do? Like, so what we're going to consider is integrating the quantum Fisher information. Naively, of course, this quantity is unbounded because you say it's t squared at any point. And of course, you imagine that there's some like bandwidth over which you'll have sensitivity and it'll fall off otherwise. But we couldn't, still haven't, besides our result, found anything saying, providing any bounds on this. So it seems like a natural question to ask, and it's going to be the one that we're going to ask. So we're going to consider the integrated quantum Fisher information. a quantity that we haven't seen anyone kind of consider before. And so that means that we're going to, instead of looking at the sensitivity just at DC, we're going to consider something like a sensitivity profile across all frequency. And so you can consider some kind of metrological protocol, like a Ramsey sequence. I've put in the sequence up in the top right in case people aren't familiar with Ramsey sequences, but it's kind of maybe one of the most obvious things you might consider doing. And you use it, for instance, when you're trying to like calibrate the frequency of a qubit, or calibrate your pulse rather, calibrate your like pi pulses. So all it is you put the qubit on the equator of the Bloch sphere, you let it precess, and then you try to bump it back up to the North Pole. And kind of based on your inability to do so, you can back out how detuning errors in your pulse that you're using, your like pi/2 pulse. But the actual sequence is just the one on the top right. It's you initialize a state. In this case, we're initializing you consider initializing the North Pole. You do a pi/2 pulse into the plus state, free precess under the magnetic field for some time, pi/2 again, and then you measure. That's a Ramsey metrological protocol. And so it actually has a sensitivity profile like this. So J is the quantum Fisher information on the y-axis. In the DC example, it's exactly what I just shared with you previously. It's 4t² for the height. And if you work out the form of the quantum Fisher information as a function of frequency, which isn't too bad because it's just a derivative, you get a sinc squared. The kind of important thing or interesting thing to note, maybe because this is like the first example you might think of considering, is that it has this kind of characteristic width around the origin of 1/t². If you actually do the integral, you just get a integrated quantum Fisher information that's linear in time. And so the intuition there is, I guess, just peak of t², width of 1/t, you get something linear in time.
And to be sure, I mean, when you say integrated, you always mean obviously frequency integrated.
Yeah, integrated with frequency from 0 to
sure.
And so you can ask the question, is this optimal? If you want to maximize the integrated quantum Fisher information, the integrated sensitivity over all frequency, is having something that scales as kind of linear in time optimal. Never mind the question of where the peak is, just is that the most broadband sensitivity you can get? So this is the question we answer. To start with, we're going to consider a discrete model. So kind of the way we're going to first kind of try to grapple with what we mean by metrological protocol is just consider instantaneous pulses that we're calling P. They're allowed to be different. There should be a subscript on that P, followed by periods of free evolution, UI, under this kind of AC magnetic field Hamiltonian. We're going to be starting in the plus state. You can almost like, you can make arguments that like, you know, it's kind of general if you start in other states, but we're not going to worry about that right now. And then you have n periods of free evolution. So you imagine something like this, your state psi is a pure state. We're not considering decoherence or anything. And it's just alternating free evolution by an instantaneous pulse, free evolution, instantaneous pulse. These free evolutions are just given by this exponential of b times this theta I function, which is of course just the integral of a cosine, because that's our Hamiltonian. And so the quantum Fisher information, again, is given by this quantity that we listed on the second slide, maybe the third slide. And so this will be relevant on another slide. I think I'll show it again when we have it. This is just computing the derivative. Basically, the point is that you have the product rule. So you get a sum over kind of these chains of P's and U's with a single Z inserted at an index, and then the theta sitting out front. And so we're going to consider computing the integrated quantum Fisher information of something like this.
Sorry, can I ask a quick question? How much of what you said and what you're going to say relies on having a closed system and a unitary evolution?
Everything I'm doing is unitary. So I haven't done any open system dynamics.
I see.
Okay. Depending on the kind of question you're thinking about.
I'm thinking about like, I mean, many scenarios, but like, I mean, in particular, like how robust is like your results to the presence of any whatsoever environment?
Yeah. I'm not quite sure. So like, this is something that I am interested in thinking about. I just haven't thought about it because thinking about things takes time. I think somehow like this still provides, like, I'm going to give you an upper bound And I think the upper bound is still going to hold, probably because you can always just like enlarge your non-unitary dynamics to unitary dynamics. But the question of whether or not you can saturate the upper bound with non-unitary dynamics is an interesting question. So
yeah, I mean, it's maybe to follow up on what Giacomo said. So there was like in the early days of sensing, there was a bit of a debate to what extent like noise would change things. And there was like a bit of a like an S-curve effect where people thought like that high entangled states would be like extremely good in sensing tasks like GZ type states. And that's kind of right. But then if you apply these states, then you realize that their scaling in the system size would be extremely bad. And people were like shocked and disappointed by that. And then later people realized that in the presence of noise, there would be like trade-offs and interesting trade-offs in that some entanglement is good, but you wouldn't have like this kind of GZ type entanglement. So the interplay of noise and kind of funny ways of state preparation is actually quite interesting. So in the sense, it can matter a lot to have noise, and the preparations will be much altered. But never mind, that was just a comment too.
Thank you for the question, though. So you imagine something like this. It's a sum. I've written it as a ket, which is kind of misleading because it's not normalized, but it simplifies the notation. So as an example, this isn't at all general, but I think it's a helpful example to think about. Just consider a state psi that's prepared by 3 periods of free evolution, and then I've written these x, y, and z pi pulses. So just about the x, y, and z axes, just a pi pulse. And we'll see what the integrated quantum Fisher information is overall frequency for this state. You can re-express for a pure state, as we have the QFI is this, just kind of an inner product between these phi terms and these and then psi phi. You can just show that, which is why I put the phi on the previous slide. Now we can talk about the details if you want, but basically, you know, commuting pi pulses through exponentials of z's is not bad at all. I have this tilde over the u because there should be a flipped sign in the exponent, but you can basically commute through the pi pulses. I'm renaming this thing on the outside just pi hat because it's not going to matter. So the kind of state of this, the final state in this case is going to be kind of these free evolutions with this pi thing outside. But maybe if you're very quick, you look at the expression I have in the top right, and when you actually compute it, the kind of thing on the outside is going to cancel. You're going to take an adjoint of pi pulses against each other. The u's are also going to kind of cancel because they're kind of exponentials of z. And a final, oh, and I guess, yeah. Okay, I jumped ahead a little bit. This is the derivative. This thing is starting on the equator. So in particular, this psi phi term, you can either look at it for a little while or take my word for it, is going to have a z expectation of 0. And so when you take this phi inner product, you're going to end up with this sum over these theta i's, which are the kind of integrals of the cosines at different times. And so this is what I was saying about the kind of pi pulses canceling and the u's canceling. You just end up with this sum over the theta I, theta j's. And the kind of nice, simple picture you get when you work out this particular pi pulse example, but kind of in general, any pi pulse example, you can kind of generalize the math a little bit. I didn't want to, I mean, this is already enough equations for a slide. Is when you integrate this, these phis, or these thetas, I'm sorry, have this nice kind of orthogonality property that if you integrate them against each other, you get like a Kronecker product, and you just end up with 2 pi t. So in this example of 3 pi pulses for some and 3 periods of free evolution, where actually the time of the different periods didn't even matter, just for total time t, you get 2 pi t. You get, again, linear scaling in the integrated quantum Fisher information, much like we did in the Ramsey sequence. Of course, the Ramsey sequence is maybe a special case of this because it was in fact pi over 2 free evolution, pi over 2 up. So it's like a measurement, an initialization of the plus state, and no pi pulses. So the kind of, I think that's a useful intuition that you get kind of for these pi pulses, you kind of get this like sum over theta I, theta j terms, and it ends up being 2 pi t. And then what you find is that actually many protocols satisfy this 2 pi t upper bound. So I told you Ramsey is like 2 pi t, kind of because it's 1 over t width, quadratic height. Any sequence of pi pulses, you end up with this kind of property, like I just said, where you have an integral over the sum of these thetas and you get 2 pi t. And if you perturbatively look at it, you get something like this, where the leading order term is 2 pi t plus higher order terms like b squared t cubed. So what I mean in particular by perturbatively is you consider a Hamiltonian, you have some control unitary that's independent of the frequency. It's just some control that lets you do like unitary whatever. And then you have, in addition, the magnetic field that you take to be a perturbation. And so that's a continuous time protocol, which you can, of course, trotterize. And that's what we're going to do in a couple slides. But the point is that to leading order, that's also 2 pi t. So a funny story is that Graham was like, you should try to prove that 2 pi t is a bound. And I tried proving 2 pi t is a bound, and I couldn't because it's not a bound. But it already suggests kind of a story here, which is you have no free quantum information. Of course, taking from the no free lunch motto. So this suggests that at least for this family of protocols, sensitivity at one frequency comes at the cost of sensitivity at another frequency. So in particular, if you consider something like a sequence of pi pulses and you have sensitivity at one frequency, necessarily there won't be sensitivity somewhere else. So if you want to build a sensor that's kind of good somewhere, the band is limited. Moreover, the perturbative result shows that if the kind of time of the sensing protocol is short and your magnetic fields are kind of weak, you're also limited to this 2 pi t regime. And so that's relevant. I think sensing weak magnetic fields is maybe a natural context to consider. Moreover, like if the coherence times of your sensors is short. Now, that's a tricky thing to say, I guess, because somebody, I didn't see their name, I'm sorry, asked about open systems. If I'm saying coherence times are short, naturally, it's somehow like an open system, right? But if you have like a characteristic time that's short, you're also limited to this kind of 2 pi t regime. Great. So I think that's interesting, but it's not an upper bound. What we show is that there's actually a quadratic upper bound, again, for unitary protocols on the integrated quantum Fisher information. And so you can show this kind of using the discrete model that I gave you before. I'm not going to provide the full proof here because it's kind of an exercise in like, calculus analysis, kind of detailed error tracking, but I'll give the intuition. If you have a Hamiltonian that has a control part, G of t, and then again, the magnetic field we're trying to sense, you can consider, of course, this is, I've just plotted the magnitude of G of t here, but you can imagine that your G somehow has an amplitude. It's your control. It's moving you through space, trying to somehow coherently, echo up or echo away certain things to sense them. It has some amplitude profile, and you can, of course, trotterize that. So we're going to do that. We're going to, again, recall that this is the functional form of the quantum Fisher information for a pure state. We're going to, again, remember that this is the form of the derivative for the discrete protocol we considered. And this is, I think, the key thing that we're going to note. If we're interested in an upper bound, the second term you can actually show is non-positive definite. So we're going to ignore it. I'm not going to prove that to you here.
You ignore it, but I just mean then you get still an upper bound by ignoring a negative term. Okay.
Yeah, it's still an upper bound. I'm ignoring a negative term. So we're going to look at the inner product of this phi term. When you take the inner product, kind of as I showed you before, you have these kind of thetas that show up. And before, for pi pulses, it was maybe very simple because of this orthogonality of the bras and kets. In general, you're going to end up just with a matrix V that kind of comes from the inner product of these strings of kind of pulses with Z's in the middle. And it doesn't matter so much, except to note that these are actually just inner products of bras and kets. So they're not going to be any more than one in norm. So it's a matrix with an n by n matrix where n is the number of pulses in your sequence. All entries are no larger than 1 in magnitude. And so you can just upper bound kind of by like a quadratic form kind of thing, like the eigenvalues are only going to be as large as n. You're going to get this factor of n out front and with the theta squared. And this is again an upper bound. We threw away the negative term, the non-positive term, and now we're just upper bounding kind of the eigenvalues of this matrix.
But is this tight in N? I mean, is this
So I'm not guaranteeing tightness here, but what we're going to show later is we're going to give an example of a protocol that's asymptotically saturates this bound. So I haven't looked at prefactors, but we'll see an example that's t squared. And so I'm kind of happy enough with that. Is that all right? Jens?
Oh, sorry, I muted myself. Yes, wonderful.
Okay, so again, you have this 2 pi nt. This is familiar. We have this 2 pi t for pi pulses, but we have this extra factor of n. And like, so now we have this continuous protocol we're considering, which is kind of general, right? But what are we going to do this n? Well, obviously, if you have an n, you just have trotterized, you get a t over delta t. So maybe the immediate complaint here is that you have a delta t that you're presumably going to take to 0 in the denominator. But intuitively, you now see this t squared factor. And kind of the work that I do in the paper is to show that you can take this delta t to be non-zero. Like, I'm going to say this in words. I haven't included a slide on it because I only wanted kind of the intuition here. You can compute the integrated quantum Fisher information of this kind of discrete trotterized approximation, and you can relate it to the integrated quantum Fisher information of the continuous protocol. And then there's an error term that kind of comes from the error in the trotterization, and you can show that the error term isn't too large. And so that all holds for non-zero delta t. But that error analysis, I don't think is particularly intuitive. I think this is the intuitive argument, that you have basically just this. You have this 2 pi nt, and n is like t over delta t. The fact that you can take delta t to be non-zero is maybe the thing that's not obvious.
Sorry, I find this formula a bit confusing. Like, can you explain what it means? That, like, I mean, it seems that, I mean, this upper bound gets squashed down the larger you take delta t. Like the
but then the approximation will be very bad.
Exactly.
So this delta t is coming from a trotterization, and what go on, sorry.
No, indeed. So I mean, like, if you think about like the integrated variance, which is lower bounded by the inverse of this integrated Fisher information, if I understood correctly, it means that the worse you take the trotterization, the better bound, like the higher your
Yeah. So
understand this.
I'm going to try to say what I just said maybe better, and then hopefully it'll make clear what's happening here. So we have a continuous protocol. We want the integrated quantum Fisher information. I'm saying, let's compute the integrated quantum Fisher information of the protocol by looking at the integrated quantum Fisher information of a trotterization. So in the limit that delta t goes to 0, the trotterization will, the error between the two will go to 0. And so you expect that this approximation to be good. If you take delta t large, the trotterization is going to be poor, and the integrated quantum Fisher information of this discrete protocol is going to be a poor approximation to the integrated quantum Fisher information of the continuous time protocol. So the extra ingredient, so naively, what that means is you want to take delta t to 0. The extra ingredient here is that, in fact, you can show that if you take delta t non-zero, you can also bound the error term between the two, and you can use the integrated quantum Fisher information of this discrete protocol to also quadratically upper bound the integrated quantum Fisher information of the continuous time protocol. Like, if I had a pen, I'd write something, but basically what I've written here is this J of, this is the integrated quantum Fisher information of some continuous protocol. If you wanted the IQFI of the continuous time protocol, it would be equal to this plus some epsilon of delta t. And so delta t going large would suppress this term, but the other term would get very large.
Well, but I mean, the problem that I see, I mean, maybe it's just a misunderstanding, like I'm not getting it, is that, I mean, the two integrated quantum IQFIs, okay? Yep. The continuous true one and the discrete model one, I mean, they coincide only in delta, as you said, and when delta t is taken to 0, clearly, when the trotterization is accurate.
Yeah.
But in this case, I mean, the bound is meaningless, right? Because it says that this thing is less or equal than infinity. And
Yeah.
I mean, which is like, I mean, and then you're saying, okay, the two things, like in general, I mean, are distant from an error which can be bounded using the error in the trotterization.
Yeah.
But it means that like either you kind of like admit that this quantity is something else, right? But what I'm saying is that like the error is gonna decrease, okay, between the two, but the value of the bound itself will increase.
The prefactor will increase, but the
Yeah.
scaling in time doesn't.
Sure, the scale, yeah, but I mean it's gonna be like a scaling times like a huge factor. So I mean,
I didn't work out the optimal prefactor for this, so that's why I've been saying asymptotic. I am interested in kind of, so what I have in the paper is some expression that just has this kind of 2 pi t squared over delta t plus an error term that's proportional to delta t among other things,
right?
Some integral, and you can of course compute the like tightest prefactor by taking a derivative and minimizing it, and I haven't done that. So I don't know what the prefactor is. I don't know how large it is. But kind of the thing that I'm interested in, the question I was trying to answer was just the scaling in time, just the functional dependence on t, not the prefactor.
Okay, thanks.
Thank you. So I think this is kind of the intuition for why you might end up with the t squared. And then the other thing we do is we just have an example that kind of gives you this quadratic scaling in time of integrated quantum Fisher information. So it's a very simple Hamiltonian. It's just we call it the transverse field, but it's really also just kind of up to a change of basis, like the kind of driven Rabi model, or like, you know, when you try to flop a qubit, you get something like this. So the kind of picture when you kind of drive this thing on resonance, which is when I'm saying drive, maybe that's not the right thing to say because we're kind of thinking about sensing, but when omega equals 2g, you kind of have this picture on the right, this GIF, where it's just the qubit, you know, spins around and then does like a pi pulse. And so I have plots here, which are numerical examples that kind of demonstrate for you this broadband behavior. So the red curve is a Ramsey pulse, a Ramsey sequence, I'm sorry, which I told you in the beginning, it's like a sinc squared. And so you see that it's like a sinc squared. It's very narrow around the origin and very tall. If you consider now the GX protocol that I have here, this transverse field, you have the black curve. And so you see that it's very broad. And so kind of, as I'll mention in the next slide, if you integrate this, you can kind of lower bound the area underneath by something proportional to t squared. And since we know t squared is optimal, we know the asymptotics are proportional to t squared. Kind of interestingly, we provide 2 trotterizations of this protocol. And so, of course, the pi protocol, you see, has these kind of, it zeroes down and ends up being less broad. That's, of course, because we know from previously, I told you that pi protocols always have this linear integrated quantum Fisher information. So the green curve kind of doesn't have so much area. But the yellow curve, the kind of lime curve, is it's already better. It's like the next order trotterization, and you can see it's already broad. So this is nice because we have this upper bound on the integrated quantum Fisher information asymptotically, just the big O, and we have an example that saturates it asymptotically. We prove, in addition to numerics, that this protocol kind of has this behavior. The intuition is that you can kind of break it up into 3 subregions. And kind of in the first subregion, you just have this kind of DC-like behavior. It doesn't really matter because you just kind of integrate up to like a constant and you can kind of ignore that. And then above some frequency, nothing much really happens. This is, of course, very hand-wavy. My presentation right now of this, we prove it.
What kind of defines these regimes? I mean, can one kind of bound the?
Yeah, so it's like basically the main thing is that you're interested like on resonant, or when omega equals 2g, you kind of, the Hamiltonian simplifies a lot. It's like kind of rotating wave approximation, and you can kind of pick out like a band where accumulates t-squared integrated quantum Fisher information. And so before that, you don't really care because it's just up to like a constant frequency and you can kind of ignore it. And above that, you see that it kind of trails off and nothing much happens. So it's basically, I think the main thing here is just that you have the rotating wave approximation near omega equals 2g. And indeed, if you look at the sensitivity of these things, it's kind of like you have a peak just at omega equals 2g, and then you have some sensitivity near 0. Which is nice because it means that like this is an example of a protocol where you can kind of tune G and you can kind of get this kind of broadband sensitivity kind of tunably. So the other thing that isn't a full lower bound, but we kind of think that there's we've reason to suspect there's like a linear asymptotic lower bound on the integrated quantum Fisher information. Of course, you have to kind of, there's a caveat on this because if you have any particular single state, you can just have the quantum Fisher information be 0 at all frequencies. You just put the thing on the North Pole and then it has no sensitivity anywhere. So if you average over the initial state, we think that it's probably linear in time. And you can at least see this for pi pulses in the same way that we prove that any sequence of pi pulses has linear integrated quantum Fisher information starting in the plus state. You just end up with another integral over the initial state, basically, if you just average over the block sphere. And so you get something like 4 pi over 3t. This isn't general, obviously, but it's interesting in the context of any dynamical decoupling protocols that use pi pulses, which is a lot of them. Because, as I'll say again at the end of this presentation, it means that you necessarily, actually, is it my next slide? It's my next, or it's this bullet point. It says that you have sensitivity somewhere if you have pi pulses, averaged over initial state. So if you imagine you're doing quantum computing and you write down a dynamical decoupling protocol where you're trying to echo away the noise somewhere, you're necessarily just going to move that noise sensitivity somewhere else.
And I mean, and that would be like the Haar average or something over the preparations, or
yeah,
what's...
it's just yeah. I'm just taking the Haar average over the initial state. Of course, this is a single qubit, so Haar average is maybe a bit heavy-handed. It's just, you know, the like uniform integral over the sphere. I don't talk about it in this talk, but if you want to generalize to more qubits, you know, I haven't proven that everything's tight, but the analysis generalizes very simply in the paper. And it's like for entangled probes, you get like factors of, you know, like n squared or something, right, for the entangled probe. And like, so if you have a system of like n qubits, kind of these results all apply. Also by things like the convexity of like quantum Fisher information, things like that. Anyway, so to conclude, I just have two kind of example slides. The first is axion detection. This is one of the motivating examples. I think when Graham was talking to James Thompson. So axions are a candidate for dark matter. I think the way that they couple to kind of the standard model Lagrangian, or at least one way they couple, is through an interaction with the electromagnetic field. And so people build, like, for instance, like Konrad Leonard at Gilla has like a superconducting system where it's some kind of cavity that you have some electromagnetic field in, and you kind of sweep over these long ranges looking to see if you can detect an axion. And so what you do is you kind of sit there, you sense for long enough, and then you park at the next frequency. So it's kind of relevant. And so what you imagine is that you have this sensitivity at each point in frequency space that you need to kind of accumulate so that you know that you successfully did not detect an axion or did detect an axion at that frequency. And so if you have some band omega that you want to accrue the sensitivity over, then if you have a protocol that's kind of like t squared height and 1 over t width, like you imagine for like a Ramsey protocol, indeed you can use kind of spins to do this, but like the conventional approach that at least Konrad uses is with cavities. So it's an interesting question of if you can get this kind of t squared behavior, this integrated quantum Fisher information of t squared in for dark matter searches. But what I was saying is that if you do something where it's like a height of t squared and like a width of 1 over t, you kind of end up with a total time that's like omega j naught 3 halves. So J naught's the kind of desired sensitivity at any point, and capital omega is the bandwidth over which you're accruing sensitivity. But if you use something that's more broadband, so like a height of t squared and a width of 1, or like a constant width, then you improve your total time by a factor of power 1, a factor of 2/3. And so like, maybe this doesn't sound like a substantial amount, but if you look at these axion detection papers, they cite anywhere from a few decades to trillions of years for axion detection. And that's because I think the way that you kind of do this is you just do these long sweeps of integration time. And the way that you pick your kind of feasible region is by looking at these like exclusion regions. It's like people have searched here, it's not here. Certain models for different parameters exclude certain things, but the search region can be extremely large. So this factor somehow matters. And then the second example, which I already mentioned, is something like noise spectroscopy or dynamical decoupling. I've talked to Jens a bit about maybe a project that would be interesting related to this, kind of tying the work I just talked to you about together with kind of CPMG noise spectroscopy. But so CPMG is Carr, Purcell, Mayboom, Gill, a bunch of people's names. It's some kind of echoing sequence. So there's an example here. It's like a bunch of pi pulses. You can change kind of timing between these pi pulses and how many pi pulses there are. And on the one hand, it's kind of like an echoing routine. That's why I have this kind of Hahn echo example in the top right, but it's generalized, of course, because there's many pi pulses. You can imagine that if you have an AC field at some frequency and you kind of pi pulse at that frequency, you can coherently amplify that signal. People, in particular, this Bylander paper, use this for noise spectroscopy. So they write down these filter functions like the one I have written here, this G thing, and they kind of have this sensitivity profile. So this isn't a quantum Fisher information, but I'm nearly certain there's like a pretty clear relationship between the two. It gives you this filter function for the pulse. So it's like it echoes, it coherently amplifies a signal at some frequency, and then everywhere else you kind of don't get any signal. And so what they do is they sweep this over frequency and they can recreate their noise signals. So they do noise spectroscopy. One reason I think that this is interesting is that these sequences use pi pulses. So I think you could maybe get a time optimal noise spectroscopy routine if instead of using just pi pulses here, you did something more interesting so that you had this kind of broadband sensitivity. Now you might object and say that you're not necessarily interested in, when you're doing noise spectroscopy, to have broadband sensitivity. You really want some high peak and very narrow sensitivity. So, I mean, this is kind of something I haven't thought about. I was talking to my friend who actually does axion stuff, and she was telling me that, you know, the broadband data, like if you do this sweep, you get information about like the overlapping areas, even in the broadband thing. So I think there's probably a way to make use of the broadband data, even if it's not just kind of narrowly peaked. But, and again, the kind of linear in time lower bound says that any of these dynamical decoupling protocols that use just pi pulses necessarily have insensitivity somewhere. So it's no free QFI, and it's also no free not QFI. But that's everything. So thank you. I'd tell this to everyone. I think somebody actually called me at TQC. Unfortunately, this is my Google Voice phone number, but I own the phone number 1IFIT-qubits. So if you want to text me, hang out with me in Berlin, you can text me there also at any of these handles. But thanks for your attention.
Wonderful. Great. That was great. Clap, clap. We had lots of questions along the talk. Are there more questions? Like, I mean,
so yeah, I have like one question. So you consider like some signal
Oh, is it me or did he break up?
multiple qubits.
Sorry, my internet I think just broke up. What did you say?
Hi. So if I understood your setup roughly, like it was like you have like one qubit and then you have like some signal that's coupling to that. Can you consider coupling to like multiple qubits?
Yeah, so if you want to consider multiple qubits, Basically, I think what happens is in the analysis that I suggested for the like discrete protocol, the free evolution periods, like you can still trotterize the protocol if you have multiple qubits that are all coupled to the field. And then in the free evolution period, you're basically going to end up with a factor of n. And then you kind of, that factor of n drops down on the derivative. You have this inner product of the derivative against itself. You get this kind of characteristic n squared term that pops out when you have entangled probes. So I think, yeah, go on.
So is your analysis, would the analysis just be analogous? Because you did this rotating wave approximation, right? And I presume you need to consider higher order terms if you couple to multiple qubits.
So I was talking about the analysis for the upper bound for the GX
Right.
protocol itself. If you wanted to show that that also was tight, or like gave you the same asymptotics or gave you this factor of n, I'm not sure. Because I did rely on the RWA.
I see. Okay.
I have maybe two questions. One is, I mean, you said that there's kind of this no free lunch, no free, I don't know. I mean, that this argument that there's some insensitivity somewhere, or sensitivity for that matter. Like, can one use this kind of to tailor the broadband protocol itself? I mean, you're not forced to be completely agnostic to frequencies. So, what's the deal here? And the other question is, I mean, all this is like fish information based, right? I mean, it's not single shot or so. I mean, it's not it's all kind of asymptotic in the analysis. And the question is, like, would that change somehow if one had like a non-asymptotic setting, possibly in the broadband aspect, in the scaling in T and everything?
You're leading the witness. The first question, sorry, so indeed, it's an interesting question of tailoring protocols based on this insensitivity. I haven't thought too much. There's another student in Graham's group that's kind of, I think, thinking about coming up with sensing protocols that kind of given this information. So somehow, like, I mean, it's extra structural information about the sensitivity band. So you can probably use that if you want to do things. I mean, like the 0th order thing that I keep suggesting is that, you know, you do like grape or something and you like try to come up with some sensing or like some Hamiltonian control protocol and you look at the sensitivity and you can probably use this broadband information to optimize. The second point you made is I haven't thought actually about the asymptotics. So this is related to another, sorry, non-asymptotics, the single shot limit. Like, I'm sorry?
No, I agreed. Yes. Mm-hmm.
Oh, like I've been working on another project that also kind of has like a metrological focus, and like, so it's interesting because like the quantum camera band also has this factor of m. Like, it's not clear to me exactly how things behave when you only get like a single shot out. Like, I just don't. I mean, I was talking to you about this a bit, right? Like, I'm very interested in exploring how this works.
Yeah, wonderful. Cool. Great. Super interesting.
Yeah, I think I have something along the same alley as Jens was asking. And I mean, how operational is this quantity that you define? Because I mean, for the regular fish information, I know I have to come around bound. If I have like a lot of shots, there's a lot of experimental repetitions, I can just do like maximum likelihood estimation. Then I'm guaranteed to get this kind of sensitivity.
Yeah.
And how does, or is there like a similar like prescription that kind of saturates a bound which contains this integrated quantum fish information?
So I think all I can say, especially on the spot, is that everything I've shown is somehow my main interest was just getting some kind of upper bound, something that I can be like, it's no more than this. I haven't guaranteed any kind of tightness anywhere except for this kind of asymptotic, you know, giving an example that has the same asymptotic. So like there's this prefactor question, which is interesting. And then you're asking about operational things. And indeed, like the integrated quantum Fisher information has this property, or like the quantum Fisher information has this property that you assume like the best POVM or something. So operationally, like in terms of like actually like single shot experiments, or, you know, I don't think I captured the full flavor of what you asked, but I don't think that I have an answer for you. Like it's, this is like
maybe I phrase it differently. So I mean, is there like a similar like integrated grammar row bound or something like this?
So
information.
there's a, I don't know if this answers your question, but there is a like a spectral Kramer-Rao bound or something in this paper by Carl Caves and someone else. So it answers like a related question to what we have, but somehow slightly different. And I think that might be, if you want an integrated quantum Kramer-Rao bound, I think that might be what you want. It somehow gives you, I mean, have you seen that paper? Oh, okay, great. So it's like they consider like the issue of like estimating simultaneously many waveform amplitudes.
Okay.
And then that, yes.
Yeah, wonderful. I had a similar question. Thanks. That was a really
I think
good.
the first author might be Manke Sang. Might be, I think it's Sang, Caves, and one other person. I don't know who else.
Cool. Very nice.